In this video, we're going to continue to look at the equilibrium constant. And first, we have to just talk about reactions in general. And in a reaction, if one of your products or reactants are a pure solid or a pure liquid, you have to realize that during a reaction, the concentrations of a pure solid and a pure liquid do not change. For example, take a gold brick. It has so many moles per volume. Let's just say, for the argument, that gold brick has a concentration of 1 mole per, I don't know, a liter. Chop that in half, exactly in half. It'll have the same concentration. I'll have one brick will have zero point 0.5 moles divided by 0.5 liters, which is 1. The other half will be zero point 0.5 moles divided by 0.5 liters, which is 1. So no matter what, concentration of solid and liquids do not change. And since their concentrations do not change, we actually don't put the concentrations of solids and liquids in our equilibrium constant. So let's take a look at this. We have carbon dioxide gas plus H2O, which is a liquid, going to H plus and HCO3 minus. While equilibrium constant is our products divided by our reactants, but we don't have any H2O because our state symbol L is saying that's a liquid, and so we don't put in pure liquids or pure solids, only gases and aqueous substances. Now let's look at how we actually use the equilibrium constant and how we can measure it. And so the easiest way to find an equilibrium constant is just measure the concentrations of your reactants and your products at equilibrium. And the thing is about this is that even though for different reactions or different trials of the same reaction, you might have different amounts of products and reactants, but that does not matter. The thing to keep in mind is that for a particular reaction at a particular temperature, the equilibrium constant is always the same. It does not matter what you start with. At equilibrium, you will always get the same ratio. And we can look at that at this example. So we have the equation H2 plus I2 goes to 2HI, and we're going to say this is at 445 degrees centigrade. In each one of these rows, we start with a different amount of H2, I2, and HI. And we also end with a different equilibrium concentration of each of these products and reactants. But let's look at Kc, and here's the equation for Kc, in case you forgot. And no matter what, Kc is always 50. So although you have different initial starting concentrations and you have different ending starting concentrations, when they're at equilibrium, you plug these equations into your equilibrium constant, you'll always get the same number for the same reaction at the same temperature. Now let's take a look at how we could actually calculate these equilibrium concentrations. And we can use stoichiometry and to do this if we know initial concentrations and at least one equilibrium concentrations of our reactants and products. And the way we do this is by using what's called an ice table. And we'll walk through on how we use an ice table. All right? And we're going to use our change in concentration of our known substance. That is, we need to know one substance at equilibrium to know how the other substances change. But like I said, we're going to walk through this ice table. All right. So our problem is we have 2 moles of methane gas that can go to 1 mole of ethene plus 3 moles of hydrogen gas. So let's say our initial concentration of CH4 is 0.087 molar. At equilibrium, we know H2 is 0.012 molar. We need to find K. Now in a reaction like this, or in a problem like this, if I only give you your initial concentration for your reactants, assume your products are 0. Alright. So to solve this, we first need to get KEQ. Well, KEQ is just products over reactants raised to the power of their stoichiometry coefficients. So C2H2 multiplied by H2 raised to the power of 3 divided by CH4 raised to the power of 2. Right? So here we need to use what's called an ice table. So an ice table, the reason it's called ice is because we have 3 different columns. We have a column for our initial concentration, we got a column for a change in our concentration, and we got a column for our equilibrium concentration. And so for our ice table, we're going to list everything that's in our equilibrium equation. And so initially, we know we start with 0.087 moles of CH4. And like I said, if I don't give you any concentration for the products, assume they are 0. Now our change in reaction. So we know based on the stoichiometry of our equation here, when this reaction happens, we're going to lose 2 moles of CH4, so minus 2x. For every 2 moles of CH4 that we lose, we gain 1 mole of C2H2. So C2H2, its change will be plus x. And we also know for every 2 moles of CH4 we lose, we gain 3 moles of H2. So the amount of H2 we get is 3 times x. And we also know at equilibrium that our amount of CH4 will be 0.087 minus 2x. Our C2H2 will be 0, that's what we started with, plus our change was x. And for H2, we're actually given how much we end up with at equilibrium. It's just 0.012 molar. Now we have enough information to solve for x, because we know for H2, we started with 0, we gained 3x, and we ended up with 0.012. So 0.012 is equal to 3x. We divide each side by 3. X is 0.004 molar. Now that we know x, we can determine the equilibrium concentration of our other 2 species, right? So CH4 is 0.087 minus 2x, which is 0.079. C2H2 is just plus x, which is 0.004. Now we have all 3 of our concentrations, and we can plug them into KEQ. So KEQ equals 0.004 multiplied by 0.012 raised to the power of 3 divided by 0.079 raised to the power of 2. Solve that mathematically, and KEQ equals 1.1 times 10 to the minus 6. So let's just take a step back. We got a KEQ that is really small. Does that make sense? And it does, because our denominator, our reactants, are much bigger than our products. So 0.079 versus 0.004 and 0.012 raised to the power of 3. So this reaction is reactant favored, so we would expect a very small KEQ, which is what we get. That's it for this video. I'll see you in the next video.